Welcome to Parents Quest number 148. We have a special one today. It's about the aerodynamics when two cars are passing each other, and I promise you'll laugh, you'll cry, you'll love it. So this study involves two armored bodies, which we have described in detail in many other podcasts. So this study is looking into the major aerodynamic features of a car and how these change when one car is passing the other. And to do this, we're going to look at a paper called A Research into the Flow and Vortex Structures Around Vehicles During Overtaking Maneuvers with Lift Force Included. So this is an open access paper. You can find it in the link in the description. So one thing to note about this particular armored body that they're looking at is that the back light, or the back window in effect, is pitched down at 30 degrees. So you can see down here. And if you're just listening to this on Spotify and or Google, you can watch the video on Spotify and or YouTube. And on YouTube, we have other goodies that you can find and learn from. So let's discuss the general wake of this armored body. And just a reminder that armored bodies are very good approximations for the major flow features of a car. So in figure 2, we see that the flow features are included. We have the outer layer. The authors say that there is an outer layer first, and this is the trailing vortex, which is denoted by the letter C. Then we have the middle layer, which is divided into two toroidal vortices, A and B. Then the inner layer is a separation bubble denoted by E. So let's discuss this in plain English. So the armored body features a very large vortex that grows along the rear side of the vehicle, one on each side. So we have this one, which is seen, but there's also another one on the other side, which they haven't included here. So this is partly due to the lift produced by this armored body, but also due to the roof angle. So this roof angle does a lot to actually help produce this and grow its strength. So this vortex is denoted by the letter C by these authors. So we actually go through all of these features, so this vortex C, A, B, and E, in our YouTube series, Automotive Aerodynamics. So if you want to watch that on YouTube, you'll learn a lot more than what we're just going through here in a few minutes. So behind the car, there is also a separation zone, and two vortices are found there, so A and B. And they are split into these two vortices that spin in opposite directions. And this is mainly due to the flow separating in this region. So you can see then the flow that comes over, it then sort of gets sucked and then it takes up that wake and then shoots downstream. So we then have the armored body with the backlight of 30 degrees. There is a separation bubble there, which we have gone through in other podcasts describing exactly what a separation bubble is. So you can find a link to a good one in the description below where we go through this in detail. And these features are what we will be looking at today, and how one car passing another car changes these features. In addition, we'll also look at how the lift, drag, side force, yawing moment, pitching moment, and pressure coefficients change. So for this study, the researchers are using CFD and they're using URANs with a realizable K-epsilon turbulence model. So one reason why this turbulence model is good here is because the Y plus value is quite high. It ranges from 20 to 40, which they say down here in this table here. So for these Y plus values, you're kind of stuck with the K-epsilon turbulence model, that family, so whether it's the RNG, realizable, or just the plain old K-epsilon. And we discussed the reasons for this in the last podcast 147. So another thing to note is that they ran the simulation in steady state first to get the initial convergence solution. Then they used that solution to then jumpstart the transient solution. So that way you can reduce the computational time as well as reducing the chances of divergence. So it's pretty interesting how they set up the CFD with these two different bodies. So they made two domains, which we can see here in figure 3, and each domain has one car in it. And these cars are located somewhat close to this interface between the two domains. So each domain was 8 meters in length, and they were 1.5 meters in width and 1.5 meters in height. They set each car a little distance from the interface between the two domains, and they varied that distance to see how that would change the aerodynamics of both cars. So this distance, in effect, tells us how close the side of one car is from the other during this passing maneuver. So for both cars, they had a moving floor, which is good because that approximates the real life condition where, like, if you don't have a moving floor and you just have like a flow going over it, you're obviously going to get a boundary layer. But when you're driving around in the real world, the car is moving and not the air. And that means that the relative velocity between the air and the street, the ground, is 0. So there's not going to be a boundary layer forming there. So that's why you need this moving wall boundary condition on the ground here. So they also had the free stream velocity set at 30 meters per second. However, while for car 1, they had the car body as stationary, car 2's body was set to be a moving wall. And the velocity of this moving wall was set to be the difference in the velocities between the two vehicles. So this isn't technically the same as real life because car 2, which is traveling at a faster speed, doesn't experience a faster free stream velocity, which it should here. So they have the moving wall, which they do say, like, so if the car is moving at 40 meters per second, they put an additional 10 meters per second on this car's body, but the friction velocity that it's surrounding it is not 40 meters per second as well. It's only 30 meters per second, and that's a problem. It should be boosted to match that. So that's an inaccuracy there. Also, they say that they're using a moving wall condition and not a sliding mesh or something akin. That means that regardless of how long they run the simulation for, the two cars will never change their locations. For example, say you start the simulation with car 1 car length ahead of car 2. So for example, car 1 is here and car 2 is about here at this -2 point. Then even if you run the simulation for like 5 minutes, after that, car 2 will never even pass car 1. It will still be at that station of -2 after 5 minutes, because there's no actual physical motion between the two. It's all witchcraft effectively with these mathematics. So what that means is that at any point that any potential transient passing effects won't happen. Now that doesn't mean that this research isn't important, because pretty much all research has limitations. It's just important to understand these limitations. So that's what we're doing here. And here we will just be getting the main effects of the passing and not the finer details. Now one thing that I want to point out for this study is that they do the grid independent study properly, which I really like. So we've had a few podcasts now where the grid independent study has been pretty dodgy. Actually, it's ranged from very dodgy to somewhat dodgy on the dodginess scale, but fortunately they do it properly here. So they have 3 different meshes. Let me scroll up a little bit here. They have 3 different meshes that they check out, and they have one thing they do change is the Y plus value. They go 40 for the coarsest mesh, all the way to 30 for the middle mesh, and then 20 for the finest mesh. Now, all these are still no good for any other model other than K epsilon, but still, it's getting better. So they found that the middle mesh gave very similar results to the fine mesh. Let me scroll down so we can see these here in this figure here, figure 4. So the middle mesh gave very similar results to the fine mesh, and both of these approximated the experimental side force and yawing moments quite well. So they're running with the middle mesh. That is the way you were supposed to do a grid independent study, where the number of cells changed quite a bit. So it went from 92,000 to 143,000 to 201,000. And the fine mesh, the middle mesh approximated the fine mesh, and the fine mesh approximates the experimental data. So that way you don't have to use too many resources, and you can just run with the middle mesh and you're fine. So let's just quickly go through this here, where they have the side force and the pitching moment coefficients, and you can see that the green line is the solid green line is the experimental results, and then the dashed ones are the CFD. And when you go to the middle and fine, the blue line collapses on itself, as does the green line. In fact, you could say that even with the green line for a coarse mesh, that it's quite close to experimental data anyway. But for the side force, you need to have the middle mesh or better. So let's move on to the Y plus values of the vehicles. So in figure 6, we can see 2 plots, one for each car. The plots show the Y plus as you go along the cars, from the front to the back. For the upstream car, car 1, the Y plus value is given in green, and you can see that at the front it is over 40, then it drops to around 25 along the sides, and finishing at around 5 for the rear. For the downstream car, car 2, we see that at the front it's quite lower, it's about 30, sorry. Then before it drops to about 16 along the sides, then ending up at about 5 in the rear. And in table 3, they give us the maximum, minima, and mean values. So car 1, the maximum, they have this mixed up actually, I'm quite certain. Where car 1 actually has a Y plus value of 44, I'm quite certain. And car 2 is 33. Anyway, the mean values are 16.5 and 24.5 respectively. So personally, I don't like Y plus values that high, but it is common to have them that high. It doesn't mean that the results will be right though, but it is somewhat standard practice. So figure 7 shows the general flow field of the 2 cars. Each car has the 2 trailing vortices, as we know from before, and the vortices are the backlight in the wakes, so E2 and E1. So let's move on to the forces and moments. In figure 10, which we will scroll down to here, we can see the whole thing, that's good. So in figure 10, we see the effects of the car spacing on the forces and moments, as well as the longitudinal positions. So in other words, how far downstream one car is from the other, as well as how close side to side they are. So for the drag coefficient, which is here in this figure 10a, the upstream car, car 1, which is denoted by the blue line, experiences a huge change in the drag. For example, when car 2 is actually in front of car 1, car 1's drag coefficient is over 0.6, which is quite high. But when car 2 drops behind car 1, car 1's drag plummets to about 0.27. So that means that depending on where car 2 is longitudinally speaking, car 1's drag could be double. So if you have car 2 behind car 1, car 1's drag dropped a lot. If you have it ahead of car 1, then it goes up quite a lot. So that means that car 2 actually affects car 1's drag a lot. But on the other hand, the distance between car 1's side and car 2's side doesn't really affect the drag coefficient that much. For example, when car 2 is located 0.5 cars downstream of car 1, so about here, moving from 0.25 car widths away to 0.7 car widths away had almost no effect at all on the drag coefficient of either car. You can see they're both around the same value as if you had the car very close. So the only time when the side distance mattered was really when car 2 was about 0.5 car lengths ahead of car 1. So you can see here that the interesting thing is that regardless of car 2's longitudinal and side positions, its drag coefficient didn't really change that much. It hovered between 0.6 and 0.8, which, okay, is about 33% difference. But compared to car 1, where the drag coefficient more than doubled, the change of 33% isn't really that much. So car 2 is kind of more immune to these changes than car 1 is. So as you might expect, the side distance didn't really affect car 2's drag coefficient that much either. So in other words, car 1, the drag coefficient of car 1 is affected a lot more by car 2's position upstream or downstream, but not by the side force, but by the side distance, sorry. But car 2 isn't really affected really by the longitudinal distance or the side distance. So moving on to the side force coefficient in figure 10b. Again, the longitudinal location of car 2 in relation to car 1 had a very large effect on the side force on car 1. So for example, when car 2 was actually 0.8 car lengths ahead of car 1, so just about here, the side force was about 0.2 for car 1. Then when it was side by side, the side force coefficient dropped to minus 0.1. So depending on the longitudinal position, the side force can either be negative or positive for car 1. I think I know why that is, and that is because when you have a car alone, then there is no side wind, the pressure on each side of the car will be equal, effectively. Like, there are some minor differences, for example, the steering wheel location, this and that, but overall it will be pretty much identical, which means that the pressure on one side cancels out the pressure on the other side. However, when you move another car side by side, the pressure on one side will be very different to the other, and hence throwing off the equilibrium and resulting in a net side force. I'd say that car 2 was affected about as much as car 1 in terms of the side force coefficients that we can see here. One thing that's interesting is that both cars exhibit the same general trends, but the opposite. So that makes sense. Like, if you were to move car 1 ahead of car 2, that's pretty much the same as moving car 2 ahead of car 1 in terms of the effects that car 2 has on car 1 and car 1 has on car 2. I know there's a lot of cars going around, but in other words, it's a symmetrical system effectively. There's just the only difference is really the moving wall condition on car 2, which is only about 5 meters per second here, which is not very much. And we'll get into later how that actually affects the results. So in this system, car 2 has the added moving wall condition, as I mentioned. And if you look at figure 10b, and you can see that if you rotate the green lines by 180 degrees, so like clockwise, in terms of the trend, it will match the blue line. So this trough here becomes that peak, this trough here, so this peak here becomes this trough, and this trough becomes that peak. So you can see it pretty much lines up exactly in terms of the trends. But the magnitudes are a little different, and that can be attributed to that moving boundary wall condition that I mentioned about. So this scenario didn't exist for the drag coefficient, because if you look back to figure 10a here, and flip the green line left to right, so left to right, the green line doesn't really match the blue lines in terms of trends. That tells us that the drag coefficient is more sensitive to the moving wall boundary condition than the side force. So let's move on to the lift coefficient, which is 10d here. So interestingly, the two cars mimic each other in that when one car is one car length ahead of the other, both cars experience a peak in the lift coefficient. So here, and about here. However, so at other longitudinal locations, the lift coefficient is largely unaffected. However, one thing to note here is that unlike the drag coefficient and the side force coefficient, the lift coefficient is significantly affected by the car's side distance. So in fact, this sensitivity is very nonlinear, and when the cars are 0.5 and 0.7 car widths apart, there is almost no change in the lift coefficient of either car. But as soon as you get the cars much closer to 0.25 car widths apart, the lift coefficient shoots up, as shown by solid blue and solid green lines here. So the reason for this is currently unclear. We'll look into the flow physics a little bit later and see if we can sort of see anything that jumps out. But first, let's move on to the effects of the relative velocity between the cars on these force and moment coefficients, which are in figure 11. So this shows the effects of, let me go down to here, so that's the legend here. So figure 11 shows the effects of different relative speeds between the cars on these coefficients. So the difference in relative speeds range from 5 meters to 20 meters per second. So in other words, car 1 is traveling at 30 meters per second, car 2 travels anywhere between 35 and 50 meters per second. So obviously that's going to be overtaking car 1. So when car 2 is traveling anywhere from, so when car 2 is traveling at 35 meters per second and car 1 at 30 meters per second, the relative difference is 5 meters per second, which we see here in these like solid green and blue lines. So the good thing for the drag, side force and lift coefficients is that the trends stay largely the same. The magnitudes change quite a bit though. For example, the drag coefficient of car 2 steadily increases as with an increasing relative difference in speed. So for example, when the cars are neck and neck, so here at 0, car 2's drag coefficient went from 0.6 to almost 1.2 when the relative difference in speeds went from 5 meters per second to 20 meters per second. This doubling was largely isolated to car 2 for some reason, while car 1 only saw significant changes when it was behind car 2, but when it was in front, no real change occurred. So you can see here and here. Now it might be tempting to think that car 2 simply had different flow physics, but the fact that car 1 didn't exhibit these same trends as car 2 suggests that it has something to do with how car 2 was set up. So do you remember when we were talking about how car 2 had the moving boundary wall condition to simulate it traveling faster, but the friction velocity it was exposed to wasn't right. It continually stayed at 30 meters per second instead of the 35 or 40 or 45 or whatever it was that the car was traveling at. So in this case, when car 2 is traveling 20 meters per second faster than car 1, it was still exposed to 30 meters per second free stream instead of 50 meters per second. However, the moving wall conditions says that the flow over the surface is 50 meters per second. So the forces it might feel are because of the 50 meters per second flow, but the wake it produced is subject to a 30 meters per second friction velocity, and I'm quite certain that these forces were non-dimensionalized using 30 meters per second instead of 50 meters per second. That means that every time car 2's relative velocity jumps up, its x-force increases, but the drag coefficient doesn't take that into account because the friction velocity it uses to non-dimensionalize was only 30 meters per second instead of 50 meters per second, or 45 or 40 or 35. So proof of that is that if you do factor in the additional velocity into the equation, drag equals half times the density times velocity squared times the cross-sectional area times the drag coefficient, so you factor that in, the velocity, into that equation, you'll see that the green lines become much closer, and if you then flip them left to right, they match the blue lines. So these green lines come much closer, and if you flip left to right, the green lines will then match the blue lines quite closely. So that indicates that the friction velocity wasn't really taken into account, the effects of that, when they were calculating these drag coefficients here. And with that, I'd say that my investigative skills are damn good, and being this good at aerodynamics should be illegal. But anyway, let's move on. One more thing to note is that the lift coefficient, which is down here in figure 11D, exhibits a similar problem in that it may appear that the car 2 is getting a greater and greater lift coefficient with increasing speed, but that is because the wrong friction velocity is being used here to calculate the lift coefficient. If you factor in that car 2 is moving faster and the friction velocity is faster, the green lines collapse on each other and approximate the blue lines again. So I've kind of had enough of these force plots at the moment, so let's move on to the flow physics. Let's see some pretty pictures instead, because car 1 is fine, but car 2 has some problems here. So figure 2, let me zoom out here a little bit so we can hopefully see all the figures at the same time. Here we go. So figure 2 is the velocity fields of the two cars during the overtaking maneuver. In essence, when one car is about half a car length downstream of the other, so for example in figure 12C or figure 12G, the car that is upstream has a significantly smaller wake. So we can see here, if we were to have figure 12A, for example, when one car is significantly downstream of the other, car 1's wake is quite big, but in the next instant, when car 1 is only half a car upstream of car 2, the wake is smaller, and here as well, and the same thing happens here. So this makes sense because you have part of the wake taken up by the other body, and that prevents the wake from the upstream car from expanding and developing. that would explain why in figure 12a we saw that the drag coefficient drops here. So in figure 12a we saw when one car was half the car was downstream of the other, the drag coefficient dropped dramatically. That's because that weight can't really evolve and take up anything. So the flow is really squished to the car and helping it stay attached pretty much. So in figure 14, we see the vortex structures of each car, as shown in figure 14a, for example. As the downstream car approaches the upstream one, the vortices on the upstream car get pushed to the side. So we can see here these vortices are fairly straight. There's a little bit of a kink here, but as car 2 approaches car 1, these vortices get pushed more and more to the side. When the cars are neck and neck, the vortices of each car keep to their respective sides. So you can see like this middle line down the middle here. The vortices don't really move past that very much. So this would also explain why the side forces change. As the wake and vortices of each car get pushed to the side, an imbalance occurs in the forces, which creates a net non-zero side force. So moving to the vortices at the rear of the car 1, back onto figure 16 here, we see the streamlines of car 1. So we can see the figure vortex A, B, and in the separation bubble E. So this is for car 1, and we see that they are mostly unaffected regardless of really where the car is in terms of car 1 versus car 2. So the top vortex remains largely for almost every distance of car 2 behind. It's pretty much the same. So figure vortex B1 here, it always pretty much stays larger than A1. And the only really appreciable change occurs for the separation bubble when the car is upstream. This bubble remains separate from the vortices in the rear. So we can see here E1 is separate to B1. But once the car falls behind, so car 2 catches up to car 1 and surpasses it, the separation point now joins the vortices in the rear. Now the authors also gave the flow physics for car 2 here, the one that starts downstream and makes its way upstream. However, considering the incorrect flow conditions, I'm not sure how trustworthy these results are. So car 1 is fine because it isn't that affected, it's more affected in an indirect way. So it's unlikely that the results are that wrong. But for car 2, I'm hesitant to trust these results or even the force coefficients because they don't take into account this change in the upstream velocity nor the even factored in for the non-dimensional coefficients here. So with that, we come to the end of this podcast. I really enjoyed it because there was a lot of complicated stuff here and some investigative work we needed to do to understand the work's accuracy. But I think we did a good job, even if I do say so myself. So if you like this podcast, give it a like. And if you want to see more like this, click the subscribe button or the follow button, whichever platform you're on. And if you want to get better at CFD and or aerodynamics theory, check out courses link in the description. And if you want to make your experiments 2 to 4% more accurate, get yourself an atmosphere hawk. It's an instrument that we make to accurately measure the density of air. The reason why this is important is because the density of air always changes. For example, if you come into your wind tunnel in the morning, then come back after lunch, the density of air has changed by 50% in just those few hours. The density of air is affected by the temperature, pressure, and humidity. So having even you in your wind tunnel changes the density of air because you're pumping out heat and you're pumping out more water from your air when you're breathing and talking. So what's more, the density of air changes even more than 2 to 4% between days, weeks, months, and seasons. So 10 to 15% changes are very normal, which means that you need to take them into account in your experiments. What's more, if you don't take them into account, then not only are most of the things you find in your experiments are just random error, but trying to use your experimental data to validate your CFD won't work, and that is one of the major reasons why so many people have trouble validating the CFD. It's not actually that the CFD is wrong, it's just that the density of air they use in the CFD is not the same as the density of air that they use in their experiments. So of course they're not going to line up. So get yourself an atmosphere hawk. It makes your experiments and CFD more accurate. You can find it in the link in the description, and I'll see you next podcast. Peace, amigos.